Did she say it's only a collarbone?
Okay. Does anybody have any questions to start with? All right, so what I thought I would do is go through, and I'm going to mix in a little bit of the background of chirality that's in the first video from Wednesday, I believe, or from Monday. And then talk about enantiomers, diastereomers. We may get to meso compounds. If we don't, we'll do that on Monday. And then on Monday, we'll talk about how to do RNSs from the different chairs and things. But before we get to that, we should probably know what diastereomers are, enantiomers, how we deal with molecules with more than one chiral center. So let me start with this, and feel free to interrupt at any point. When we have one chiral center in a molecule, we can definitely make its mirror image. And one chiral center is relatively straightforward because you have 4 different groups attached in order to have the ability to exist in the handed forms, left hand, right hand, the chiral forms. We haven't really defined exactly what enantiomers are, so we should probably do that at this point. So when you have your 4 groups attached, you can make the mirror image. And that set is a pair of enantiomers. And enantiomers are basically mirror image. They're mirror image isomers, and I usually add in front of that, I say they're non-superimposable. Non-superimposable mirror image isomers. So that means they're mirror images, but they cannot be superimposed, which is what the words mean. So basically, you need to have 4 different groups attached to a single chiral carbon. And we've learned that the configuration, the term configuration means, or we've talked about configuration with RNS, let's specifically define it. Configuration is the exact 3-dimensional structure around the chiral carbon. And the way we define the configuration is either R or S. And so that's why we needed the Coningal pre-log sequence rules. That's why we need to go through the whole process of assigning every single chiral carbon as RS. When a molecule has just one chiral carbon, it's either R or S. Okay? So what does that mean? That's the exact 3-dimensional structure, but how does it manifest itself? If I have 2 molecules with a single chiral carbon, how do I know that they're chiral to begin with? How do I know what kind of physical and chemical properties are different for a set of enantiomers? Okay. And so in terms of the physical properties of 2 enantiomers, they both have the same physical properties. Same boiling point, same melting point, shoot them into a GC, 1 peak, unless the GC has something special about it, which I'll talk about next week. Refractive index, the same. Put them on a TLC plate, you get 1 spot, unless something special is about that TLC plate. So enantiomers have exactly the same physical properties except one. And that's how they interact with plane polarized light. So what is plane polarized light? Well, if you can imagine that you have electromagnetic radiation, it operates as a sine wave, and then it also operates as having two components, a magnetic vector and an electronic vector. And so those are orthogonal or perpendicular to each other. And so that's what electromagnetic radiation looks like. There's two sine wave functions of it. A polarizing filter will take all of those different orientations of the electric and magnetic field vectors. So what's coming out of the lights right now has all 360-degree orientations of those vectors. If you pass them through a polarizing filter, the polarizing filter acts like a picket fence. And it allows only one orientation of the light to pass through. So when the light goes in, it's got all 360-degree rotations. When it comes out, it just has a single rotation. Okay. It's a physics thing. That's all we need to know. Now, where do you get polarized lenses? You can have them in your glasses. You can have them in your sunglasses. You can have them stick on your cameras if you still have cameras. And what they do is they then will block out they'll give you the ability to control polarized light. So if you've ever, light that hits a surface, like a surface of a car, or surface of the road, or surface of the water, when it reflects off, it comes back polarized. So if you have polarizing sunglasses and you kind of twist your head, you'll see the intensity of the light change as you move your head. Same thing's true for the sky. The blue color is polarized. So if you want to know if you have polarized sunglasses, just look at the sky, move your head back and forth, and if you see the blue color intensity change, you have polarized lenses. Take two of those and align them orthogonally so that the first one only allows orientation this way and the second one only allows orientation that way, and it completely blocks the light. And there are some YouTube video links on Wednesday's folder. So polarized light's been around since the 1800s. People have been able to make it. And so what Pasteur found, the same Louis Pasteur that invented milk, what he found was that if you passed a sample of your chiral molecule, if you passed plain polarized light through it, that depending on the enantiomer, it either rotated the plane polarized light clockwise to the right, which you call dextrorotary, or to the left, which is levorotary. And there's a certain number of degrees, and we'll talk about specific rotation next week, as well as talking about it in the lab, because we're going to do 2 experiments with chiral molecules in the semester. Oh, Louis Pasteur didn't invent it. I know that. I used that joke the first time I was teaching in Kansas, and the smoking group outside the building had to corner me and go, he didn't invent milk. And I go, I know, it was a joke. Well, we can't tell when you're joking. So I always tell that joke again. So Pasteur was the one that linked the idea of this chirality to plain polarized light. And how he did that was, Pasteur did a lot of things. But he's in France, wine everywhere, wine growing everywhere. What wine growers and people, I guess, who drink wine knew was that sometimes when you take the cork off the wine, there were crystals that had grown on the cork in the inside of the bottle. And there were 3 kinds of crystals. And so he got these crystals. The legend is he painstakingly separated them with tweezers. And the 3 different kinds of crystals were one where it was symmetrical. So it had what we're going to call later a mirror plane of symmetry. So symmetrical crystals. That people called racemic acid at the time. The other crystals were mirror images of each other. So you could align them and they were perfect mirror images. So he got all these crystals, he separated them out into 3 piles. He knew about plane polarized light. He didn't discover it, but he knew about it. And for some reason, he decided, I'm going to make a solution. I'm going to pass plane polarized light through these two mirror image crystals. And that's when he found that one rotated to the left, one rotated to the right. And if you mix them 50-50, they cancel each other out. So that led to the idea of chirality. And there might be some controversies along the way because everybody wants to make sure that they get credit for all of this stuff. So they go back and they find their notebooks and their notes during that time. But that's the legend of Pasteur and how he discovered, or linked actually, chirality to plane polarized light. So we have a D form and an L form. D just stands for dextrorotary. It means you have a positive rotation clockwise. Levorotary, L, means the rotation is to the left. One of these two is D, and one of them is L. Now, the problem is that no matter how many chiral centers a molecule has, there are only two mirror images. Okay? So if you have 26 chiral centers, there's only two forms that are left and right-handed. Now, what are the other, numbers? We'll talk about that. But in this case, either the R is D or the R is L. There is no correlation. People have taken all the known correlations. They tried to do some big data manipulations, and there is no real trend per se that holds in every single case. So if you make a chiral molecule, or if you have a molecule that exists in one-handed form, it's easy to tell whether it's D or L. You take it to an instrument called a polarimeter, which we'll use in lab. You pass plane polarized light through it, and you figure out, does it rotate clockwise or counterclockwise? Piece of cake to do that. Not so much a piece of cake to determine the exact three-dimensional structure around the carbon. That requires that you slowly crystallize the sample and get a perfect crystal, which is not what we've gotten in labs so far. We got plates, but a perfect crystal would be something that's like a perfect cube or a perfect 2x4 shape. It would be perfect where all the atoms are stacked in that crystal structure in exactly the same orientation. So if you get one of those crystals, and if you get it for a small molecule, or if you get it for a large molecule like a protein or DNA, right? The whole DNA controversy about Watson, Crick, and Rosalind Franklin. We were just having this discussion in lab yesterday with the women in STEM buttons. There's a controversy there. They all contributed to the structure, but that was determined, the DNA structure was determined by getting a perfect little crystal passing X-ray beams through it. So you can do that for small molecules, and if you know what you're doing, you can actually tell, is it R or is it S? And so you can get the exact three-dimensional structure. And then, of course, you get the exact three-dimensional structure. You still got to put it in a polarimeter to figure out what the correlation is. And every single chiral drug that's developed has to go through that test. So we're going to work with Naproxen Sodium, Aleve, which you can buy generically in the name brand. Right? It's the cheapest chiral drug I can find. There are other things like L-DOPA and D-DOPA. Sugars, there's L and D sugars. There's L and D amino acids. Right? So that L and D term is in biology. And so that's what it stands for, sort of. But when we get to sugars, there's actually biochemists define L and D differently, and you can take biochemistry and figure that out. But it doesn't mean plus or minus. But sugars are chiral. They exist in D and L forms. There are enzymes that are made up of chiral molecules. Amino acids that make up a protein are chiral, so that means the protein's chiral. So all these biomolecules have the ability to exist in chiral forms. If you're going to make a drug, nowadays you have to test both forms. You have to test the D and the L form. And the reason for that is because there have been some horrendous drugs where the D or the L has done one thing good and the other one's done something horrible. Thalidomide, which is a sedative in the 60s. I saw pictures on the elevator earlier this week about children with no arms. That's what one of the enantiomers of thalidomide produced. The other one was a sedative. And so it's actually a drug that's still being sold for, I think, different kinds of cancer treatments. It better be sold as the one form only. And when it gets in my stomach, well, not my stomach, but when it gets in somebody's stomach, it better not change to the other form. So there'd be a liability issue there that your lawyers might have an issue with, Hannah.
They sold it for morning sickness too.
Yeah, they sold it for a lot of things, and then all of a sudden found out the horror of it. So nowadays, well, as far back as I can remember here, nowadays you had to actually test both of them, and you actually had to show that the other enantiomer didn't have a more positive effect when it was introduced. And then there's the whole thing, drug companies will patent one-handed form, and then when their patent runs out, they'll use the other one if it does the same thing. There's controversy about patent manipulation and all of this stuff, big profits, big drug, big pharma. But we won't go into that today. So every chiral drug that's sold, you have to make the distinction between R and S and D and L. And it's not easy to do. The crystallography I did crystallography as a postdoc. When I was a graduate student at Duke, the guy who was our X-ray crystallographer worked for the original crystallographer, which was Jack Dunnitz in Scotland. He had done drug chiralities, found a lot of them were reported wrong when they were first done. He did Taxol, which I think I've shown you, the big Taxol molecule. He determined the crystal structure of that and all the chiral centers. There's like 20 of them, whether they were R or S. It's a very interesting guy. Was amused, but that I, as an organic chemist, wanted to learn crystallography, and I went off and did a postdoc, and I learned some pretty practical stuff from him. The math I stayed away from. So that's what goes into a chiral drug, but the ultimate thing is there's only two-handed forms, and with one chiral center, it's either R, S, or D and L, but there's no correlation. So that correlation has to be made for you. You can't just look at a molecule and say, that's R, it's going to be D. Might be, might not be. The Aleve tablet is sold as I won't write its entire structure, but it's sold as a deprotonated carboxylic acid with a sodium on it. That's why it's called Naproxen Sodium. It's the carboxylic acid salt. When it gets into your stomach, with the acid that's in your stomach, it turns into a carboxylic acid called naproxen. Well, the chiral center that's over here somewhere is S in both cases. Nothing happens to the chiral center. And one form will take care of my headache, hopefully by the end of class. The other form has some issues with liver toxicity. So we want to make sure that we eliminate the liver toxicity enantiomer and that it doesn't change into that form when it gets in my stomach, which hopefully they've done. Okay. So hopefully it's just working on my headache and not my liver. But they're both S. But we're going to find in lab that the sodium is L because it rotates negatively. And then when we add acid to it and we isolate that compound, which is called naproxen, it's going to be positive. So some S's are positive, some S's are negative. So there's no direct correlation. And you'll be reminded of this when we get to that experiment, that there's no correlation. So when you have a single chiral center, it's easy. When you have multiple chiral centers, though, it's a little bit more difficult. Because now every single chiral carbon can be R and S, but there still is only a pair of D and Ls. Okay? And so that's a little bit of the practical stuff that we need to know as we go into multiple chiral centers. What else do we need to know about this? So if you mix them 50-50, that's called a racemic mixture, which I believe comes from the original racemic acid that was found as the molecule that had the symmetry on the wine cork. Although the symmetrical molecule that comes out of the wine cork is actually what's going to be a meso compound. And we'll talk about meso later. So racemic mixture is a 50-50 mixture of enantiomers. So the physical properties, the only thing that's different about enantiomers is the way they rotate plane polarized light. Not helpful. Because if I do a reaction and I make a 50-50 mixture of my two compounds, how do I separate them if the only physical property difference is plane polarized light? So we'll get to that next week. Chemical properties of enantiomers. Well, the chemical properties of enantiomers may be different or they may be the same. They may be different if they're reacting with another chiral molecule. They will be the same if they don't react with a chiral molecule, or if they're reacting with a non-chiral molecule. So they're the same if the molecule they're reacting with is non-chiral. They are different or could be different if they're reacting with chiral molecules. Here's the example. Here's a physical example from hands. So when it starts snowing here in a couple weeks, like right around Halloween, we'll probably get a big snow. It's just Cleveland. Then you'll break out your winter gloves if you have them. And gloves are chiral, hands are chiral. Right? So my hand is going to have a different reaction with the right hand glove than it will with the left hand glove, because the two gloves are chiral. Did everybody see the right and left-handed boxes of gloves up in the lab? Right? We just got one box of gloves. Right? And those gloves basically don't have, well, the thumb is perfectly in line. That's what makes them achiral. So glove in the lab fits both my left and right hand because it is not chiral. Okay? So that's a practical example of chiral reacting with other chiral, chiral reacting with non-chiral in the lab glove case. Practically in drugs, the thalidomide is another case. Any molecule, any drug molecule that gets in a biological system, proteins, enzymes, all of these things are chiral. And so one enantiomer might react differently with the other chiral molecules in your system, and one might react in another way. Thalidomide, sedative, birth defects. There are other things like L-DOPA and D-DOPA. One works, one doesn't. Aleve tablets, liver toxicity versus headache removal. So each chiral drug, when it gets in a chiral environment like a biological system or a physiological system, can react differently. And so that's a huge chemical difference between enantiomers. Okay? And that's why it's important in biochemistry. That's why it's important in biology and pharmacology, physiology, all of that, is that it's about how chiral molecules react with other chiral molecules. That's the essence of your lock and key, right, that they still teach in biology. You have the small molecule comes in and fits perfectly. Well, part of that is not only the shape, but whether it's D or L. Okay. So that's the difference in physical properties of enantiomers and the difference in chemical properties. Okay. And that's a huge issue. That's why the pharmaceutical companies have to do all of this testing. And there's a lot of chemists paid more than I make in the pharmaceutical companies to analyze and to think about these things. And that's why the process of going through all the trials has become necessary. It's not the Wild West anymore. So let's do two chiral centers. Because we have enantiomers as our relationship between molecules. Let's do two. Now remember from last time, this is what is called a Fischer projection. Okay. And the Fischer projection, the horizontal positions are bold towards you, and the vertical positions are away from you. Now, where you will see the most Fischer projections is in sugar chemistry, where we begin to draw molecules like this, with 2, 3, 4, 5 chiral centers. Okay. So let's do that with this molecule, or let's do that with this one. I'm just going to put the bold and then the dashed wedge in here. And let's say I'll put an OH here, I'll put an H here, I'll put a methyl group here, I'll put a chlorine there, a methyl group here, and an H. So I'm going to make molecule A that has two chiral centers. Now, can we write its mirror image? Sure. Mirror plane, blank structure, that would be the mirror image. And now we just draw the mirror image. The methyl group that's on the right now goes on the left, the OH on the right, the H, the Cl, the CH3, and the H. So here's molecule B. A and B are mirror image isomers. Are they superimposable? No. You might say, but what if I take the B molecule and I rotate it and I slide it into A? Well, if I rotate B around 180 degrees, all those bold wedges become dashed, and even when I slide them over here, I now have an OH, but one's bold and one's dashed. So they don't match up. So these are non-superimposable mirror image isomers. They are enantiomers, but they have two chiral centers. Okay. Now, that's just two of the possible molecules for this. In general, there is a formula of 2n. That equals the total number of isomers, and we'll say stereoisomers. And I'm going to add one more term. It's the maximum total number of stereoisomers. And what's n? N equals the number of chiral carbons. So, if you have one chiral carbon, 2 to the first, 2. DLRS. You always have DL for a mirror image pair. 2 chiral centers in this case, 2 squared is 4, so I got 2 of them. I have 2 of the structures here. I still am missing 2. Okay. Some drugs might have 10 chiral centers in them. That means you've got to get all 10 of the 2 to the 10th possible number of isomers in order to get that drug. Which is pretty amazing considering the fact that when we go out into the field and we grab things like little sea urchins or pieces of coral or plant barks right? And I've been through the sea urchins. They don't last very long in the lab. So we go out and we get all these things and we look for potential anti-tumor drugs or cancer drugs. We find one that has like 10 chiral centers, but it's only that particular structure. So nature, whatever nature is pretty specific when it puts together the molecule with the chiral centers. Because sometimes only one will work. And we can't kill all the sea urchins to cure cancer. And we can't strip all the bark off the California yew tree to get Taxol to treat ovarian cancer. So we've got to somehow figure out how to synthesize those molecules with exactly that chiral center. That's a level of detail that we'll get to later on, but we're not going to start there. But that's how difficult this stuff becomes after a while. All right, so I need 2 more. So how about I do this? I'm just going to draw another Fischer projection. I'm going to put the bold wedges in just because I want to. How about I take the top carbon off of A and I pair it up with the bottom carbon off of B. And now I make a new molecule C. So I haven't have structure yet where the 2 methyl groups are side by side or eclipsing, because that's what they're doing. Can we write the mirror image of C? Sure. Which I did not do. There we go. So there's D. D is now the mirror image of C. Okay. So we have 4 molecules. In this case, none of them are superimposable. And so what do we have? We have A and B are enantiomers. What are C and D? They're enantiomers. But now what is A and C? Or what's A and D? Or what's B and C and B and D? What's the relationship between those molecules? They are not mirror images, and they are not superimposable. So they are non-superimposable, non-mirror image isomers. And they need a different term. And the term that they're going to get, so the relationship between B and C is they are diastereomers. If you switch a couple of letters, diastereomers. So diastereomers are, all these are the same structural isomer. Right? These are all different stereoisomers that differ by their 3-dimensional arrangements. So the diastereomers, what's the relationship between A and C and A and D? They're diastereomers. So what? What does that mean? Well, what's the physical property differences between diastereomers? Everything. Diastereomers are different molecules. And so if they're different molecules, they'll have different physical properties. Now, some of the physical properties might be very similar, but they're different by definition. Enantiomers must have exactly the same physical properties, but diastereomers are different molecules. They have different physical properties. They have different chemical properties. And we'll see a little bit of this next week, because one of the examples I would show you in terms of diastereomers would be if I take a benzene ring and attach it to an OH with a methyl group on it, and I then have another carbon with a hydrogen over here and a CH3 and I have an NH with a methyl group on it. And I erase there. And I erase the CH3 and I put an H there. That is the structure. One diastereomer is pseudoephedrine, and the other diastereomer is ephedrine. Okay? Two different diastereomers. Pseudoephedrine is what you have to go to the pharmacy counter to buy if you have a stuffed up nose. You can only buy 3 grams of it a day according to the Methamphetamine Control Act of 1990, which limits the amount of pseudoephedrine you can buy because pseudoephedrine is a precursor to methamphetamine. A lot of chemistry that goes into that, but you can watch like Breaking Bad for all the chemistry there. That's why you only can buy 3 grams, and if you ever run in the woods where there's a lot of blister packs open, you should probably leave because that was a methamphetamine campground. There's other things you should look for too, like red matches, red phosphorus matches. The synthesis is relatively straightforward, but it will not be covered in this class. It's covered on TV. So pseudoephedrine stops your stuffed up nose. It's also a stimulant. Ephedrine is an even better stimulant. It was used in weight loss until they found out, you never want to use a stimulant for weight loss because it raises your metabolism, which your heart has issues with, until eventually your heart just says enough, right? And then you have a heart attack and die. So that's why fast heartbeats are not good. Right, my thyroid is gone because it was hyperactive, and I'm like, okay, well, you're stressing your heart out. What isn't? So anything like that, those stimulants they took off the market. There was fen-phen and stuff like that. Ephedrine is gone. You can't get ephedrine. It's controlled substance. But these two are diastereomers. If I have a GC and I'm a forensic chemist, I can inject those 2 compounds into a GC and see 2 peaks. I can put them on a TLC plate, see 2 spots. One melts at like 35, another one melts at 100. So diastereomers are completely different molecules. They have different physical properties and they have different chemistries. They have different chemical reactivities. So diastereomers they're separate molecules. So if you come back here and you look at these 4, A and B are enantiomers, an enantiomeric pair. C and D are an enantiomeric pair, but the rest of the relationships are all diastereomers. So a single molecule with 2 chiral centers is going to have 1 mirror image and 2 diastereomers. There are far more diastereomers than there are enantiomers for a molecule simply because there's only 1 enantiomer. There's only 1 mirror image. So in this case, these are the 4 structures for this molecule. Okay. Now, that's great. What's the relationship in R and S in these molecules? So we can go through here and we can assign the R and the S configurations for each of these carbons. So let's start with this one right here. My number 4 group is hydrogen. My number 1 group is hydrogen versus carbon versus carbon versus oxygen. Oxygen's number 1. How about a CH3 versus a C with a lot of other stuff on it? This one would be number 2, and this would be number 3. Okay. And as you do more and more of your RS problems, you'll get to the point where it'll be like CH3 is either number 3 or number 4. It can be number 4 if there's no hydrogen. What I like to do with this is I like to pull this chiral center out and sort of draw it, and then I put the numbers in like 1 and 4 and 3 and 2. So that way I don't put numbers down here in the molecule and get confused as to which number goes with the chiral center. So in this case, is 4 pointing away from me? Yes. In a Fischer projection, all you have to do is get number 4 on a dashed wedge. Which dashed wedge? It doesn't matter what dashed wedge. It's on a dashed wedge. How's the best way to do that? Probably group switching. Because we'll talk about Fischer projections next week. There are certain things you never do with a Fischer projection. Group switching avoids that. Okay, so is 4 away from me? Yes. Now, as you do more and more RNS problems, practice problems, you want to take that second to make sure that 4 isn't on a dashed wedge. Our usual, operation is switch or rotate 4 to the back. But if 4 is already in the back, you want to make sure you don't undo that. So in this case, 4 is on the back. Going from 1 to 2 to 3 is counterclockwise, so that means this chiral center is S. So what's the chiral center in B? It's R. What's the chiral center in C? S. What's the chiral center in D? R. Am I that good? I am. But did I determine R and S for every one of these from scratch? No. S, mirror image, is R. We kept the top in C, the top one was the S again, and then we drew its mirror image R. Right? So if you're sitting there going, he's a super genius, not quite. Not even close. Patterns, right? Okay. So first thing that we learn is when you take a chiral center and you make its mirror image, what happens to the configuration? It becomes opposite. S becomes R and R becomes S. Okay, bottom carbon. If I take my bottom carbon here and I separate out my my chiral center, hydrogen is 4. Who's number 1? Here. The chlorine's number 1, then CH3 versus a C with more stuff than CH3, and so that would make this number 3 and this one number 2. So here's my orientation. First question to ask is 4 away from you? Yes. Okay. 1 to 2 to 3 is? It's counterclockwise. Bottom carbon says. Yeah, as you're doing RNS configurations, notice there is a lot of places that you can make mistakes. Will you get the right answer if you make a mistake? You could. Right. Did I use the 2 wrongs equals a right? Could equal a right in this class? I'll have to do that in the Monday end. So you could make 2 mistakes and get the right answer. So you want to take a step back. Make sure 4 is behind you and make sure your clockwise, counterclockwise directions are okay. Right? There'll come a day when there is no more clockwise and counterclockwise, because we won't have these clocks anymore. Everybody will go digital. And then what will we do? We'll survive. Okay, so let's do the same thing with BCD. So the bottom carbon of B is going to be the opposite because they're mirror images. Let's see, I took C's bottom carbon from B, so that's an R, and then mirror image is S. So why am I doing this? Always a good question to ask. Now what we could do is now we can look at the relationships from the R and the S standpoint. So what about enantiomers? In a pair of enantiomers, what is true about about the configurations of the chiral centers? Each and every chiral center is that was anticlimactic. S becomes R, S becomes R. Every single chiral center becomes or is opposite. So in a pair of enantiomers, every single chiral center in that molecule is opposite. Okay? That's true for one chiral center, it's true for 30. Every single chiral center is opposite. What about diastereomers? Well, B and C are diastereomers. RS, R, R. So for diastereomers, what I like to say is at least one chiral center is the same, and at least one chiral center is opposite. So at least one of those is the same, at least one of them is opposite. That is a then universal rule that covers two chiral centers up to as many chiral centers as you want. At least one's got to be the same, and at least one's got to be opposite. And that's what makes diastereomers. And so a lot of times we can base our diastereomers on that basic principle. Sometimes we'll do R and S to determine that. Sometimes we're going to look at the two chiral centers and we're going to say, oh, those are the same. Oh, the other two chiral centers, they're opposite. These molecules are diastereomers. So those are the fundamental definitions as far as the individual chiral centers go. All opposite enantiomers. One opposite, one same, diastereomers. Because at some point next week we are going to play the game, are they enantiomers, diastereomers? Are they the same but they're not meso? Or are they the same meso compound? And so I will give you a pair of molecules and you'll have to figure out what the relationship is. Okay. So that's the basic relationships for these chiral molecules. They're enantiomers or they're diastereomers. We can now go into molecules that have two chiral centers. And we can describe their relationship. And we can talk about whether they have the same physical properties or not, whether they have the same chemical properties or not. And we'll do this with chairs, we'll do this with Fischers, we can do this with Newmans, we can do it with just a single chiral carbon. But single chiral carbons are boring. Now, one other thing, in order to have a pair of diastereomers, you need to have at least two chiral centers. If you do not have two chiral centers, you can't have diastereomers. You can't have that. Everybody kind of with me here? And I probably did the exact same thing in one of the videos earlier that's on Canvas, because I do the same thing, except today I mixed in more of the practical chirality. Here's what I would like you to do for Monday. We'll call this practice, or we'll call this graded problem. I would like you to do this. I would like you to take this molecule A, and it has two chiral centers. So I would like you to take this molecule, and I would like you to write molecules B and C and D like we did before.
Do you want us to identify RNS?
Oh, I'm not done yet. So the first thing is I want you to write B, C, and D. Then I want you to identify the R and the S configurations for each of those chiral carbons in those molecules. And then what I'd like you to do is to sort of classify the relationships between the molecules. Like what's A and B, what's A and C, what's A and D. Now, is there a twist to this? Yes, there is a twist. The twist is that two of those are going to be the same. For two of those, they will be superimposable. Okay. You may have to rotate the molecule around, but you will find that two of these are the same. And the two that are the same are going to be called a meso compound. Okay. So that's what I would like you to do for Monday. We'll start with this problem. Then I'll define meso, although you can look in the textbook. So in Top Hat, we're kind of behind on the reading assignments. So I'm going to update that today, and I'll send out an email for Monday. But this is a time, if you didn't do the Top Hat problems up to this point, up where we're at now, you can go back and fill those in. I will have your exams on Monday. They will get done. They haven't been done. This is the problem with Monday exams, is I've got to somehow grade them throughout the week, which didn't happen, so I'll get them to you on Monday. I will not release any scores over the weekend. I will not. I'll release the answer key on Monday for it, because I remember one year, apparently somebody sent out a text message to somebody else. He just released the scores, and then there was like, I don't know, apparently there was a lot of buzz about text messages going back and forth. The scores are available. They will not be available. I will not put them online. I will not put them for you to see before Monday. That avoids the Jill incident, where the student who became one of my research students, I shorted her 100 points on the score that I put online on Canvas, and apparently it caused some crying and some mental anguish. And then when I handed her the exam, she's like, "You put 100 points less online." And I said, "Okay, did this cause you a lot of mental trauma?" And the person standing next to her was like, "Yes, it did." So I don't put the scores, I don't release the scores until after I've physically handed them out to you. Okay? We'll see you on Monday.